It is a pleasure to welcome you to second edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on mechanically stabilized earth walls, which will be delivered by Professor Emeritus Richard J. Bathurst and Ms. Yuli Dulala Rigby. Dr. Bathurst is Professor Emeritus of Civil Engineering at the Royal Military College of Canada, where he has taught since 1980 and holds a cross-appointment at Queen's University. He is a past president of the Engineering Institute of Canada, Canadian Geotechnical Society, International Geosynthetics Society and the North American Geosynthetics Society. Dr. Bathurst has authored or co-authored more than 200 journal papers and 250 other contributions. He has made contributions in the areas of micromechanics of granular soils, railway ballast and track dynamics, pavements, unsaturated soil geotextile behavior, constitutive modeling of geosynthetic soil reinforcement materials, new test methods and the development of transparent granular soil surrogates for geotechnical testing. Dr. Bathurst's current research activities are focused on geosynthetic and metallic reinforcement in earth-retaining wall systems, numerical modeling, seismic performance and design of these systems, probabilistic design of reinforced and unreinforced soil structures, reliability-based design, and load and resistance factor design calibration of soil structures. Dr. Bathurst has served on committees of the Canadian Highway Bridge Design Code and the National Building Code of Canada. He has received national and international awards for his technical contributions and has been invited speaker and keynote lecturer at Learned Society conferences and symposia on many occasions. Dr. Bathurst is editor-in-chief of the peer-reviewed technical journal Geosynthetics International and associate editor of the International Journal of Geomechanics. He is fellow of the Canadian Academy of Engineering and the Engineering Institute of Canada. Dr. Bathurst was elected fellow of the Royal Society of Canada in 2017.
Yes, so thank you, Dr. Mishra, and your colleagues for inviting me to give this lecture. I'm honored because I looked at the list of people that have gone before me, and it's quite a distinguished crowd. And I'm also happy to give this lecture back to back with Yuli Dulala Rigby from Tensar, who is a longtime personal friend of mine. Okay. So I was starting by reminding everyone here that mechanically stabilized earth MSE walls are constructed with inextensible steel or relatively extensible polymeric reinforcement. And this technology has been around for some time, so it's mature and proven. If we go back in time, the first substantial reinforced walls were constructed with steel strips. And this particular slide that you see here is the first example. So the first substantial walls were constructed in France using steel strips. And this slide is very important because it shows the first steel reinforced soil wall constructed with concrete panels. And today, these types of systems are built routinely, and some of them are quite impressive, including this steel strip reinforced wall that was part of the SeaTac airport runway expansion near Seattle in Washington State, US. Starting in the late 70s and into the 80s, high performance polymeric reinforcement materials were invented, including woven geotextiles and geogrids and many other types. And these materials were then available to construct MSE walls. The first types were quite simple. They involved placing horizontal layers of reinforcement and then wrapping them around at the front to form the facing and then tucking them back in. So this was particularly efficient way of making MSE walls, although arguably not very attractive. This wall here shows the largest wrap face wall of its type, at the time that it was constructed in 1989, you can see that it's about 13 meters in height, and you can clearly see the wrapped faces or layers. And this was used to contain one side of a preload at a construction site in Seattle. It was a temporary structure, and that's why the wrap face was okay. Here is an example of a wall closer to home for me. They look like to civilians to be conventional tiered gravity walls. But if you were to look at the inside of this structure, what you would see is that these concrete panels are supported and attached to layers of geogrid. The geogrid layers are fastened to flaps of geogrid material that have been cast into these concrete panels at the time that they were formed. Nowadays, we see the use of modular block units to form the facing. Most often, the blocks are made of dry cast or masonry concrete, if you like, and these blocks are stacked to form the facing and tied back with horizontal layers of reinforcement. And the facing, the reinforcement layers, and the reinforced soil form a composite gravity mass which acts to resist the retained soil that is behind it. The first substantial wall of this type was in Canada was constructed in 1988, and it was a 7-meter high wall. But this was the first structure of this type that I got involved in, and it precipitated a long relationship with this type of technology. Now, this wall may be familiar to some of you. This is the Barney's Point wall, which was part of the support for a bridge abutment at a location about 104 kilometers south of you folks. And if you look at the inside of this structure, what you'll see is that it's a tiered wall. You can see the different tiers. And the bridge deck or bridge beam is seated directly on top of the reinforced soil mass. And this was one of the first applications of this type. And I must say it was pretty brave because this was built about 1993. Other types of reinforcement materials that have come onto the market are polyester strap type reinforcements. So these are strips that are typically woven back and forth, as you can see here, but they perform the same function as continuous sheet geosynthetic reinforcement materials, performing the same MSE function. So what we're really interested in this presentation is the internal stability limit state design of these systems. And these methods that are in use today are essentially variants of the classical tie-back active wedge method. And what folks have done, including myself, is that they have empirically adjusted the predictions of load on the reinforcement based on measurements. But the basic procedure is to assume that the reinforcement acts to tie back a wedge, which will be clearer to you in the next slide. And these design methods are packaged in different ways. So for example, in North America, these design methods are framed within a load and resistance factor method, LRFD, but in Europe and in Australia, they use a partial factor approach. I'm not going to get into those type of details. We're going to focus mainly on the mechanics of what's going on with respect to internal stability of these systems. My presentation is going to focus on the calculation of the maximum tensile load in the reinforcement. And this is the load side in internal limit states, including the limit state for internal rupture of the reinforcement or overstressing, failure at the connection between the reinforcement and the facing, and pullout of the so-called tieback wedge from this resistance zone. So we're most interested in how do we calculate Tmax. Now, until recently, our ability to accurately predict these design loads Tmax in reinforcement layers under operational conditions was lacking. So I'm not interested in the loads at failure. I'm interested in the loads that will be in the reinforcement during its design life under serviceability conditions, if you like. And what we discovered very early on is that the tieback wedge methods that were in place a number of years ago tended to be very conservative with respect to the calculated Tmax values, particularly for geosynthetic reinforced soil walls. And in addition, the distributions of tensile load didn't increase linearly with depth as one would expect for simple wall configurations. And I'll touch back on this a little later. So how do we know this? We know this because myself and my colleagues collected over a period of about 3 decades, measured loads from instrumented field walls, including both steel reinforced walls and geosynthetic reinforced soil walls, although my talk will focus mainly on geosynthetic structures. And so we collected data from carefully instrumented full-scale walls, including, for example, this modular block wall that was constructed at a Federal Highways Administration test site near Chicago in the late 1980s. And it's a modular block wall. And on the right-hand side, you can see reinforcement, the facing units, and a hint of instrumentation in the wall as it was being constructed. And from these instruments, particularly extensometers and strain gauges, we were able to deduce what the strains in the reinforcement were during construction, at end of construction, and after a surcharge was placed on this wall to about 2 meters in height. You saw that very high wrap face wall in Seattle. Well, this wall was very important as well because it was heavily instrumented as well. And during construction and at the end of construction and surcharging, strains were recorded from strain gauges mounted on the reinforcement layers, and then the tensile loads in the reinforcement were deduced from those strains. Oops. Here is a propped panel reinforced soil wall that I was involved in the early 1990s. This was the first prop panel wall of its type in Canada. And this wall, you can see the cross section here on the left-hand side, is constructed from reinforced concrete panels cast off-site, taken to site, and then propped up on end. And then the reinforcement is attached to the back of the wall. And here you can see some pre-stressing arrangements. And the wall's built up from top to bottom. And here you can see one of the instrumented layers, and these are protected strain gauges on this particular layer. So how do we calculate the predicted loads in reinforcement layers? Well, the essential procedure is to assume that each layer of reinforcement is responsible for carrying a certain portion of the horizontal lateral pressure acting against the back of the wall. And so this lateral stress acting over a contributory area for each one of these reinforcement layers is calculated simply by multiplying the vertical stress due to the soil by some coefficient of lateral earth pressure, which we can call Kr. And then we can multiply the spacing, the coefficient of earth pressure, and sigma v to get T max. And the essential procedure is that there are various charts of this type here, which show the distribution of this K factor normalized with the active earth pressure coefficient Ka. And from this chart, we can calculate what K is and then calculate what T max is for each layer. Now, it turns out that for current methods, if you like, the K factor was assumed to be Ka, the active earth pressure coefficient. And that's why you see this line here at 1. Now, what happened was we were then able to compare the predicted values, which are the values on the bottom horizontal axis that you see here, against the measured values. And if you had a perfect model, then all of these data points would cluster along this one-to-one correspondence line, but they don't. What we found was that on average, the measured values were about 1/3 of the predicted values. This is on average. And this led us to conclude and to make the statement that these simplified wedge methods were excessively conservative. Now, we collected measured loads from both steel and geosynthetic reinforced walls. For the steel reinforced walls, and these included strip type and bar mat types, as just two, or ladders, as just two examples. And it's fairly easy to deduce what the tensile loads are in these walls under operational conditions, because you just slap on some strain gauges, and knowing the modulus of the steel and its cross-sectional area, etc., it's easy to deduce what the load in the reinforcement is. And then we did the same thing that I showed you for the geosynthetic reinforced walls. We calculated the predicted load for each of our measured loads, and then we went to design charts, the same design chart that I showed you before, which tells you what this normalized coefficient of earth pressure should be with depth below the top of the wall. And you can see for steel, for example, it's a bilinear curve. And then again, you take off from this chart what this value of Kr should be to calculate T max for each layer. So we had a measured value, and for each measured value, we were able to compute a predicted value. And for the steel, on the left-hand side here, you can see that the data wasn't too bad. For geotechnical data, this is pretty good. The comparison of measured to predicted values seemed to cluster quite tightly about the one-to-one correspondence line, which was very different from the geosynthetic wall cases, for which there was a lot of scatter. And on average, the measured values were much lower than the predicted or calculated values. So why the better prediction accuracy for steel reinforcement? Well, the reason is at the very start of the steel strip reinforced wall technology, the inventors of this procedure empirically calibrated measured loads from their instrumented structures. Whereas the geosynthetic reinforced walls in the early days, they just assumed that the soil was at an active state, according to Coulomb or Rankine theory under operational conditions. And one of the reasons for this was that in the early days of this technology, there were no instrumented structures in which the measurements could be used to empirically adjust the predicted loads based on what was measured. And so these loads couldn't be adjusted the same way that the folks that developed the steel reinforcement were able to do. Now, geosynthetic reinforced walls are complicated systems. First of all, they comprise soil, and let's admit it, soil's difficult. You know, it's three-phase material, and even physicists won't touch soil, okay, because it's so complicated. Yet we have to deal with it on a day-to-day basis. Furthermore, extensible polymeric materials are rate-dependent materials. That means their stiffness, if you like, is a function of strain, time, load. So very complicated. So let's make it even more difficult by having a variety of different facing materials. They can be hard facings like the concrete panels and modular blocks that we saw earlier, or they could be wrap face, much more flexible system. And then there are complicated interactions between these components. So the expectation of coming up with a simple theoretical based model for the design of these systems is really hopeless. We have to rely on empiricism and measurements. Now, to better understand these systems, there's a need to carry out carefully controlled laboratory full-scale wall tests in addition to field structures. By carrying out carefully controlled and conceived full-scale tests in the lab, we can pick apart the mechanisms and the behavior of these systems more easily than field walls. And for a number of decades at RMC, we carried out a complementary experimental program where we built full-scale test walls in a specially manufactured test facility that you see here on the slide. Basically, it's a very large soil box, and here you see the front of a test wall. It's a modular block wall. You can see a hint of connection load cells that connect the reinforcement to the facing, and then there's a surcharging system at the top. Here you can see construction. This is looking, we're sitting inside the test facility looking towards the back of the first row of blocks in a modular block wall. The technician is pouring sand in place, and you can see the lubricated sidewalls of the test facility that were used to try and get close to plane strain conditions. Here you can see a view that shows one of these walls about a third completed. And here you can see the reinforcement layers. You can see extensometers. Here we can see load cells and other instrumentation. And we built a series of walls, and here's the control wall. So you can see the modular block facing, strain gauges, extensometers, displacement gauges, connection load cells, and load cells to measure the horizontal and toe loads on the base of the reinforced soil wall, earth pressure cells. In fact, there was over 300 pieces of instrumentation in each one of these structures. Oops. And in the first phase of this program, we built 11 walls, and the walls varied with respect to type. So some were segmental, some were wrapped. They varied with respect to number of reinforcement layers, the polymer type of the reinforcement, the strength and stiffness of the reinforcement. So the idea was that we varied one parameter, if you like, in each subsequent wall from the initial control wall, which is identified as wall number 1 here. So here's control wall 1. Okay, 6 layers of reinforcement, etc. And then we built other walls, including this wall here, which is exactly the same, except the facing batter is at 25 degrees from the vertical as opposed to 8 degrees. So this allowed us to see what is the effect, the isolated effect of the facing batter on the loads that are generated in the reinforcement. And this wall here is a wrap face wall. We've seen pictures of those before. Here you can see the wraps. And so we essentially, we replaced the hard-faced wall, which is shown as a silhouette here, by a simple wrap face construction. And what this did, it allowed us to isolate the influence of the flexibility of the facing on the loads that were generated in the reinforcement layers. Here is another wall, and here this facing comprised of incremental concrete panels, okay, arranged in a vertical orientation. And I mentioned in that table that we use different types of reinforcement materials. So for example, we had polypropylene, polyester, and we even investigated the effect of stiffness by using a welded wire or reinforcement. So this allowed us to investigate the effect of reinforcement stiffness. Now here are pictures of 2 of these walls side by side. This is me here for a sense of scale. So these walls were 3.6 meters in height. Now I want to say that we are not the only ones that were building full-scale walls. My long-term friend and collaborator, Dr. Yoshi Miyata, who is at the National Defense Academy in Japan, has also been engaged in this type of work. And I remember when I first told him about what we were doing, he said, "Oh, well, maybe you should see what we're doing." And they were building similar types of instrumented structures, except they were bigger. They're like 6 meters in height. And we've been fortunate to collaborate on writing up and understanding the behavior of these walls. And here you can get appreciation of the size of some of these test walls that they have built in Japan. And the interesting thing in Japan is that if you have a proprietary wall system that you want to sell into the marketplace, the Japanese require that you build at least one of these walls at full scale in one of the government laboratories, instrument it, and convince the agencies in Japan that the system works. And this has generated a tremendous amount of data, which Dr. Miyata and I have had the privilege of writing up in a series of papers. So what are the lessons learned from these laboratory full-scale tests and these instrumented and monitored field tests? Well, here's a whole list, and I'm not going to go through them one by one. That would be terribly boring. So what I'm going to do is I'm just going to pick a couple of these bullets here that summarize some of the important lessons that we have learned. The first one of the ones is that if you purposely take a reinforced MSE wall to failure by surcharging, the failure of the soil and the reinforcement seldom, if ever, occurs simultaneously. And when you do limit equilibrium type of analyses with Coulomb forces and all the rest of it, this observation is a violation of concepts of limit equilibrium, where all the resistance contributions are assumed to fail simultaneously. And I can demonstrate that to you by looking at the results of some of the tests that we've done. So here you see the test facility on the bottom right. And I mentioned to you there's a surcharging system. So after the walls had been constructed, there was a system of airbags that we could inflate at the top of the wall, and they were constrained by a series of beams that you can see here. So on the left-hand side, we have a record of the height of the wall with time during construction, And then after construction, we surcharged it. So the pressure acting on the bottom of the wall was about 180 kPa, which is about 3 times higher than the weight of the soil, the pressure of the soil at the end of construction. And after the tests were over, we would take the surcharging system off. And what you're looking at is the top of the soil mass behind the facing of this wall. And if you look carefully, what you see here is a failure scarp at the surface. And you can also see some cracks at the location of the back of the reinforced soil zone. Oops. And if you take an oblique view, you can see this slumped area, and then it flattens out. And there's even a crack through here. I wonder what that is. So what we did is we excavated the reinforcement in thin lifts from the top surface. This is after it's been surcharged, in thin layers, like an archaeological excavation. And we were able to trace and follow a failure surface all the way down through the reinforced soil mass. And we observed that the peak strains in the reinforcement at the time that the wall failed were reasonably aligned with this observed failure surface, which is consistent with simple tieback wedge methods of analysis if you assume the system is at collapse. And the Coulomb failure plane was reasonably in sympathy with the observed failure surface that we followed down this wall during excavation. And here is a layer of reinforcement which has been exposed carefully during excavation. And here you see this line here is the failure surface that we were tracking, but the reinforcement is still intact. And in fact, the soil failed before the reinforcement. So this was, proof of the notion that the soil and the reinforcement don't fail together. The reinforcement is too flexible. The soil is much stiffer. Another lesson we observed was that maximum loads often occur at the connections, that is between the reinforcement and the back of the wall, rather than at locations predicted by that assumed internal failure surface that you saw on the previous slide. And again, we have proof of this by looking at our failed walls, and this is an incremental panel wall. You see the cross section on the left-hand side with the incremental panels, and this photograph on the right-hand side shows the wall buckling out when it finally failed. Now, I mentioned to you earlier that we had load cells which allowed us to measure the connection load between the reinforcement and the panels at each reinforcement location, as you see here highlighted in the red circles. And when we measured the strains in each of these reinforcement layers, we got profiles similar that you can see here. So each one of these subplots is showing the strain in the reinforcement versus distance from the facing. And interestingly, you can see that almost in every case, the maximum strains are close to the connections. Why is that? Well, the reason is that during construction, there's compaction, a little bit of settlement of the soil, particularly as the facing moves out. So the relatively vertically rigid facing stays in place, but the soil moves down, and this imposes parasitic loads on the connections. And these are impossible to predict using limit equilibrium methods. Now, one would say, well, that's an artifact of your experimental technique. Well, in fact, we have observed the same thing for instrumented reinforced soil walls constructed in the field, in actual production walls. So this is a wall that was constructed with layers of reinforcement, heavily instrumented. And after the during the monitoring, we were able to pick up the distribution of strain from the back of the wall towards the tail of the reinforcement. And again, you can see that the connection forces or strains are the largest. Another observation that we made is that, you know, the reinforcement does not creep to rupture under constant load in practice. You know, we make the assumption that the reinforcement, if you leave it there long enough, will creep and finally rupture. Well, that same wall that I just showed you, we were able to monitor the strains in the reinforcement during construction, okay, and after the wall had been completed. And these are strain records for different layers in the reinforcement. And after the wall had been constructed, we continued to monitor these reinforcement layers for up to almost 2.5 years after the wall had been constructed. And the strains in this wall were higher than typical. They're up to about 2% strain. And but they seem to increase with the log of time. But this slope is so shallow that it will be thousands of years before we would get to a rupture strain for these materials. So creep in reinforcement layers in walls under normal operating conditions and strain levels, you know, it basically levels out and is not normally a problem. A very important lesson that we learned from these tests is that the tensile loads in reinforcement layers under operational conditions are a function of the reinforcement stiffness, not its strength. And I could give many examples of that, but I'll choose to show you the results from an interesting pair of walls that were recently tested in Japan. And here you see a cross section of these walls. So they're concrete panels. You can see the reinforcement, and they were surcharged. And there's two of these walls. The only difference between the pair of walls was that one half had these PET strap reinforcements, which are polymeric materials, which are relatively extensible compared to steel strip reinforcement, which was used in the other wall. This slide here shows a in situ connection test being carried out on this extensible polymeric strap material. And side by side, what you see here are distributions of tensile load in different reinforcement layers for the steel strip wall and the PET strip wall. And if you look at, you know, if you do a side-by-side comparison at similar heights, you can see, you know, clearly that the loads in the steel strip are higher than the PET strap. And that's because the steel is very much stiffer than the PET strap material. So what are some of the practical consequences of what we have discovered for geosynthetic reinforced walls? Reinforcement loads under operational conditions are less than loads predicted using, you can say, current limit equilibrium based methods. And this led to excessive amounts of reinforcement, sometimes by a factor of 2 or 3 times. Equally important, we found that the reinforcement is not distributed in an optimum vertical arrangement if you assume that the loads in the reinforcement are going to increase linearly with depth, which is the old-fashioned way. And the problem with this over prediction is that it means that the model is bad. And when you have a bad load model, it becomes almost impossible to calibrate these design methods for LRFD or partial factor approaches using reliability-based limit states. So how do we fix it? So what you see at the top is what I've called the current simplified method. And here you see this formula that we've seen before that just says the maximum load in the reinforcement is proportional to the spacing, vertical stress, and some coefficient of earth pressure. And quite simply, what we did is we corrected this method by introducing a number of empirical correction factors backfitted to measured load data. And this method is called the stiffness method. And it has a number of empirical factors that take into consideration the stiffness of the reinforcement, the flexibility of the facing, whether the soil has cohesion or not, the facing batter. All of these things that we know are contributors to maximum load are included in this new stiffness method. But the signature feature of this stiffness method is the stiffness of the reinforcement. Sorry, I'm working in the dark here. So what you see on the left-hand side is the old simplified method. And we saw this slide before where the measured and predicted values are not in alignment. And then the stiffness method, which is the new method, you can see that the data is much closer. So this equation that you see here looks pretty scary, but for most walls, you can get rid of or eliminate some of these factors, and you end up with an equation in which you really have only 3 additional empirical factors in the calculation of Tmax compared to what we have been doing in the past with the simplified method. And the procedure again is to assign to each reinforcement layer a portion of the distribution of lateral earth pressure. And what we found was that the distribution of lateral earth pressure follows a bilinear distribution rather than the sort of triangular distribution that we are perhaps most familiar with. And this distribution that you see here, which is bilinear, is captured by this this DT max factor that you see here. Now, how do you keep the walls at working stress conditions? Because remember, we're interested in operational conditions. If the strains in the reinforcement were to get too large, then what would happen is the soil would fail. So we carefully looked at our database, and we were able to find that if you keep the strains in the reinforcement to say somewhere between 2 and 3%, then the soil in the reinforced soil mass will be under working stress conditions. If you let it get higher, you will see signs of failure like cracking and slumping. And in fact, you can generate a continuous failure surface through the reinforced soil mass, which is consistent with failure of the soil. Under working stress operational conditions, we don't want the soil to fail. So how do we know what that strain is? Well, we predict what the maximum load is using our simplified stiffness method. And then knowing what the stiffness of the reinforcement is, we can calculate what the strain is and make sure that that strain is not larger than about 3%. And if you do that, then this new simplified stiffness method that I've talked about will then apply to your design for internal stability limit states. And where can you get this stiffness value? Well, you can, we fortunately, just recently, we've collected all of the stiffness data that we can for a huge range of products, and we've classified the products into different types. And what we were able to find is that there's a practical linear relationship between stiffness and strength of the reinforcement. So for a particular product or a group of products falling within the same classification, there is a useful relationship that will allow you to calculate what J is. Knowing J, the load, I can calculate the strain. And here's the front page of this paper, which just coincidentally was published just a couple of weeks ago. So I'm particularly proud of it with my graduate student, Fahima Nafchali. But does the stiffness method work? Let's imagine for a moment that we have a field project, and I'm going to design it using the stiffness method. How well is the method going to work? Well, fortunately, myself and Tony Allen, who is the chief geotechnical engineer for the state of Washington in the United States, we had the opportunity to design a pair of walls at the location of an approach fill for a bridge. Okay, so the bridge is sitting behind the slide, and here you can see this approach fill, and here's a wall on one side and a shorter wall on the other. So we're able to design that wall, those pairs of walls, and also instrument them, and then compare our predicted loads to what we observed. And this was the same wall actually that I showed you earlier. So here you can see one of these walls. It's quite substantial, 11 meters. And here you can see the instrumentation, etc., that I mentioned before. And here's a comparison. Now, when this was done, we were using a version of the stiffness method, which we called the K-stiffness method at that time. This particular method has been evolving with minor changes with experience and data over a period of about 15 years. But the essential outcome that you see here is the vertical scale is depth of the layer below the top of the wall. And the black symbols are the measured loads in the reinforcement. Now, if we use the simplified method, the old method, the predicted loads are way the heck out here. But when we use the precursor K-stiffness method to the current stiffness method, you can see that there was much closer correspondence between measured and predicted loads, and we didn't have this constant linear distribution that you would have predicted using the simplified AASHTO method. So this, in addition to this design method, which gave us more accurate estimates of the measured strains and loads in the reinforcement, less reinforcement was required. And in fact, the savings in reinforcement material for these two walls covered the cost of the instrumentation. And the other thing that was shown in this structure was that the reinforcement strains were all less than 3%. The highest were about 2%. And this is consistent with the notion of working stress conditions that I mentioned earlier are a prerequisite to keep these structures under operational conditions. So the impact of what we have done over a period of years is that this stiffness method has replaced the current simplified method in the US AASHTO LRFE design specifications for geosynthetic walls. And in Canada, in the next edition of the equivalent code in our country, the Canadian Highway Bridge Design Code, we will adopt this method as well for geosynthetic reinforcement. I should also say that this stiffness method works both for steel and polymeric reinforcement. It's the beauty of the method is it's seamless across stiff and extensible reinforcement types, and including polymeric strap materials, which are somewhere between really extensible geosynthetics and steel. So it's sort of like one-stop shopping for design using this method. However, the difference in accuracy is less between the old method, so to speak, and the simplified method and the stiffness method, because I mentioned to you before that the simplified method for steel reinforced walls was initially calibrated at the time that the steel reinforced wall technologies were first developed. That concludes my talk, and I'm happy to take any questions.
Let's take this one to start with. So Howard says that, how does the stiffness of the foundation affect the strains that you find in the test, laboratory and field? In India, he was involved in an Reco wall that underwent 1100 millimeter of foundation-based settlement during construction. They used steel strips, not geosynthetics, which at that time in 2004 was not favored by the government highway department.
Yeah, well, the one thing I should say is that when we developed this test method, what we were trying to develop was a method that applies to a baseline case in which there are no extreme loading events. The foundation is competent, and so you do your design. And if your field situation diverges substantially from a competent foundation approach, then you're going to have differences. But this is a baseline. It's a nice place to start. Now, what we have found, we've actually done tests where we did reduced scale model tests with compressible foundations, and we've also done numerical modeling. And if the foundation becomes very compressible, then you can you can get additional loads in the reinforcement beyond the load levels that you would expect using our method. But it's very complicated. A lot of it depends on how stiff the facing is in a vertical direction, how stiff the footing is that's supporting the facing vis-a-vis the stiffness of the reinforced soil, and vis-a-vis the relative stiffness of the foundation. These things all come into play. For example, we found that in some cases, these reinforced soil walls will actually rotate backwards if the foundation soil is compressible enough. And that can actually reduce some of the loads on the reinforcement. So there are a lot of interesting things that can happen. Sometimes the only way that you can explore these things is to use some numerical models to give you a sense of where things are going to go.
The next question is from Jay in ACOM, New Zealand. Can the stiffness method be applied to seismic conditions? Is there any additional factors that needs to be considered for this case?
Yes. What we do with seismic is we do the same thing that we have done in the past. Is we design the wall and predict the loads for the static case, and then we superimpose additional loads on the reinforcement using Boussinesq theory or whatever, or pseudostatic dynamic loads, and we just introduce them, add them to those loads. That's the best we can do at the moment. I think it's quite conservative.
Michael asked that the talk focus on strength. Does the reduced required reinforcement for the stiffness method have any significant impacts on the serviceability movement of the structure for the design scenario?
Not really, because we haven't seen that. You know, we're reducing the amount of reinforcement, but we're also putting the reinforcement in a better location. The main effect, the main factors that influence wall deflection are typically related to quality of construction. And this simplified stiffness method that we developed was based on walls that are built with good quality control. That's our baseline. It's impossible to come up with a design method that incorporates the quality of construction or assumes the quality of construction is bad. I mean, it's just bad policy. But we haven't seen any serious problems. You know, we've written papers, we've collected a bunch of data for measured walls, and basically what we found is that for these geosynthetic reinforced walls, typically the out of vertical alignment is, you know, doesn't get more than about 1.5% if the wall is well built and you don't have foundation problems. But that's a very good question.
There are a couple of questions around Tmax. So essentially, can you describe what methods did you use for measurement of Tmax, and if you can use finite element modeling to determine Tmax for the geosynthetic elements?
Yes. What we did is we have the strains and the reinforcement. Sometimes we had strain gauges that we had to correct for global strains, because strains on polymeric materials strain gauges can sometimes create a hard spot. So we carefully calibrated the strains so that we knew what the global strains were. And then we calculated what the stiffness of the reinforcement was, you know, from creep tests for that strain level and load. And from that stiffness value, and I basically showed that slide where if you tell me what the load is and you tell me what the strain is, I can figure out what the stiffness is, or go the other way. So that's what we did. And then when what was the second part of the question? Oh yeah, numerical modeling. Well, I just recently gave a talk which showed how high quality physical tests, such as the ones that I showed you here, can be used to establish the veracity of numerical models. What I showed in the RMC wall tests is that we had, you know, 300 pieces of instrumentation. We measured all the boundary pressures and loads and displacements, as well as the strains and the reinforcement. And it took us about 5 years to develop numerical models that could produce those results. And this is something that very few people do. You know, usually what you find is people have, you know, a single strain gauge in the middle of a piece of grid in the middle of a wall. They'll get their numerical model to predict that strain, but you never know if that model is predicting other performance features correctly, like boundary loads, etc. So one of the advantages of our test program was that we were able to develop numerical models, typically using program FLAC. And then with the verified model, we then took our RMC walls to greater height, okay, and investigated their performance. And we were able to then numerically simulate other reinforcement materials as well. And so we were able to develop a larger envelope of test results, if you like, beyond what we were able to do in the lab. You can imagine that this physical program of tests was quite expensive and time consuming. And that's true. There are a lot of graduate students who spent time helping to build these walls. So I hope that helps.
Now, Harold asks an interesting question. He says that how do we ensure that we are mobilizing the tensile strength of the reinforcement and that the mobilized strength is compatible with the soil strain around the reinforcement?
Um, that's an old-fashioned view of what's going on, because these walls are not at failure. The strength of the reinforcement is immaterial. If you design these walls for operational conditions, the soil is not at failure, and neither is the reinforcement. What is important is the stiffness of the material, and making sure that all the strains are low enough. It's a little bit like elastic plastic theory. What you don't want to do is you don't want any of your components to get into the plastic zone. You want everything to be in the elastic zone. That's a crude analogy, but that's what you want to do. And so in the early days, there's a huge amount of practice where everybody was trying to get the strength of the soil to match the strength of the reinforcement, but that's not important for serviceability conditions.
Charles would like to ask that if you can please comment on the aging effect of the geosynthetics for projects with design life of up to 100 years.
I think that the durability of these geosynthetic reinforcement materials is fairly well established. We calculate an allowable tensile load, which is a function of creep, chemical contact, this type of thing. And these geosynthetic materials are highly engineered materials. They are quite durable. And in addition, in design codes, like for example, the AASHTO or the Canadian Highway Bridge Design Code, there are limits on the properties and the gradations of the soils that you should be using. Now, I happen to live in a part of the world where these high quality fill materials are easily available. In other parts of the world, this is not always the case, and so people are building these walls successfully with lower quality fill materials, if you like, cohesive frictional soils. And the real problem with those materials, or potential problem with those materials, are things like creep, getting saturated with water so they lose their stiffness and strength, and this type of thing. But durability should not normally be a problem for these geosynthetic materials. Now, maybe Yulia will talk about the influence of temperature, et cetera. So there's sometimes there can be some issues with walls that are built in hot places, and the the temperatures at the connections, et cetera, can get higher. That can be an issue. But having said that, there is a body of work which has shown the effect of temperature on the properties of these polymeric materials as well. So we can, adjust somewhat for temperature effects.
Now, Deepak would like to say that one of the observations was that the peak strain mobilized was around 1%, and that geosynthetic reinforcements typically reach the peak tensile strength in the range of 10 to 12%.
Right.
So if the discrepancy in the strain explained by the difference in tensile strength mobilizer in confined versus unconfined tensile strength of the reinforcement.
Okay, the first thing is most walls that we have monitored, if typically the maximum strains are about 1%. So the comment was made, we know that if we put these materials, say a geogrid, into a tensile test apparatus at about 12% strain or whatever. But the thing is that you never get up to that level in practice. And in some ways that's telling you that these systems are, very safe. because the strain levels are quite low. The effect of confinement on grid materials is negligible as far as we can make out. We have done careful tests in this regard. You know, within our ability to measure the effect of confinement on these materials, it's really not detectable. Where you do get a difference is if you have geosynthetic materials, particularly non-woven geosynthetic materials, then you can have an effect. In fact, the difference in the stiffness can be, 300% in some cases. But for these geogrid materials, it's not an issue as far as we can measure.
The next question that we have is a bit general one, but perhaps you can share some of your views on that. So what is the importance or role of adding admixtures to stabilize the soil in different geotechnical projects? And what is the best method to improve the MSE walls?
Yeah, well, what people have added, for example, cement, even sometimes some polymer additives that it's almost like a cohesion, and this can be used to improve the properties of the backfill soil. The Japanese like this method, so soil cement method. They like it because it allows them to ensure that the reinforced soil mass and the reinforced soil walls, which are often used as integral abutments for bridges, act as a monolithic block of material, which they prefer to have in order to be seismic resistant. So these soil cement can, have been used successfully. I forget what the content is, 3% or something like this. So that has been used. And it also adds labor. I mean, that's, to get a uniform mixture, that's, it's takes some effort.
We have several other questions, but we are running out of the time. Are you happy for taking a couple more?
Oh, absolutely. I'm at home.
Okay. So again, one question from Charles is what would be the most possible failure mode for MSE walls: internal failure, external failure, global failure? And he points out that there was a large MSE wall failure in Turkey.
Yes,
recently.
Yeah, I saw that. And based on the commentary for the wall that just failed in Turkey in a most spectacular way, I might add, it was, as far as I can see, it was a steel strip wall, but the problem was water. Basically, when a MSE wall fails, typically it's got something to do with water. Water has ponded and then got into the reinforced soil zone or behind it, or it's scoured the base of the reinforced soil wall. It's always water, and that's what happened at this wall, as far as I was able to read about that case study. And there's been not lots, we don't want to say lots, but there have been other spectacular failures as well. And usually it's got something to do with water. In controlling surface water, it cannot be overstated in order to ensure that these walls behave themselves. But it's the same with conventional walls as well. I mean, they can perform badly as well if they are subjected to harmful groundwater or surface water conditions.
The next question is if there is any standard which is applied globally for the reinforcement.
Well, most countries have, test standards. A lot of countries adopt ISO standards, or in North America, we tend to adopt ASTM standards. And when it comes to the properties of geosynthetics, these standards are quite advanced and well established.
Okay. There is a series of questions from Harry. Harry asked if there is any attention for the drainage system for the MSE walls.
Yeah, I think you need to stop the water from ponding on top of the wall. So you need to make sure that surface water is directed away from the top of the wall. Often there's a vertical drainage layer that's placed behind the facing that will take any water that does get behind the wall down to the bottom of the drainage layer. And then there should be some form of, geopipe to then take that water and direct it beyond the boundaries of the structure. Sometimes you have to construct an interceptor chimney drain arrangement at the back of the reinforced soil zone, again, to keep any groundwater from getting into the reinforced soil zone. These techniques are well established, and if you look at Federal Highway Administration guidelines and similar guidelines, they have all sorts of schematics that will show you how to protect you from ingress of water.
The next question he has is that the backfill material is usually granular material, but how do you deal if you have to basically, if you encounter clay or a clay-like soil? Do you have to pay any special attention for this?
Yes, you do. For example, in Japan, where they don't have the benefit of easily accessible and large quantities of select granular material, they tend to use cohesive frictional soils. But you don't want to use very plastic clay materials, because this has all sorts of problems. It can be hard to compact. It can be creepy, and also it can be poorly draining. So you have to be very, very careful when you use these materials. And I've seen some failures where, in my own country, where they stretched the limit and used cohesive frictional soils with about 25% fines in them. And what happened was that water got into this backfill over a period of several years, and the failure happened several years after the walls were built, and it could have been prevented if they'd kept the water out. So the combination of so-called cohesive backfills and water could be a recipe for bad performance.
How do you integrate the effect of temperature into the stiffness method?
Normally, once you get into the reinforced soil zone, the temperatures tend to be quite stable. The only place typically the only place where it's a concern, and this is what I hinted at before, and Yuli will be able to answer this question later today, because she's quite interested in the problem of when you have these polymeric materials attached to a concrete facing, and that concrete facing is being heated up by the sun in the Sahara Desert. What is that doing to the stiffness of the reinforcement? And the best that we can do at the moment is that people have done creep tests on these materials at elevated temperatures. And so you can, from this type of testing, if it's available to you, you can estimate what the stiffness of that material might be at elevated temperatures. But right now, what's done in North America, they sort of look at the ambient temperature history, at a site, and then what they do is they take sort of an average, plus a certain percentage to estimate what the sort of design temperature for that wall is going to be. The details I don't have at the edge of my brain at the moment, but if you look at these design guides, they do give some guidance. But generally, if you get about a meter inside a wall, the temperatures will be quite constant. We've measured the temperatures in these reinforced soil walls in Canada, where it can get quite hot in the summer and bloody cold in the winter. But right deep down inside, within about a meter of the facing, we found the temperatures were fairly constant year round. Why animals like to build homes in soil.
We'll perhaps conclude with this last question. What's the difference in steel reinforcement and geogrids in terms of using them in MSE walls? Which reinforcement is better in your opinion, and why?
Okay. First of all, I have no preferred or preferences for either type. To me, they're a continuum. You know, they go from very stiff to more extensible. So it's just stiffness. However, from a practical point of view, because steel reinforced walls, the steel, because steel itself is stiffer, you might expect less deformation with a steel reinforced wall compared to a polymeric reinforced wall, where everything is equal in terms of the facing and the layers, etc. So I often tell people, if lateral deformations are an issue, maybe you have a structure nearby and you don't want to impinge your wall to impinge on it, then you might want to go with a steel reinforced system. But other than that, I have no preferences for one over the other.
With that, I would like to close this session, unless Richard, you'd want to say something to the audience.
No, I just want to reiterate again that I'm very glad to have had the opportunity to give this lecture. My only regret is that I wasn't actually in Australia. I have been to Australia a number of times, and I'm always worried that someday I'll go down there and never want to come home again. So perhaps we'll see each other at the international conference.
Hopefully, that's the hope, that the travel restrictions ease by that
Right.
time, and we'll be able to see you. So thank you again, and we look forward to see you all in 4.5 hours time from now. Thank you.